Welcome back. Good morning. So welcome to the lecture 3 of p-adic functions on ZP. So I'll start by having some sort of comments about what we talked about yesterday. So last time we kind of end with this theorem, where we talk about this exponential function, p-adic exponential functions, where this exponential of x is defined to be 1 plus x, just like the usual Taylor expansion, 1 plus x plus, excuse me, 2x squared plus maybe 2 factorial, of course, and then go on as this, and then somehow it turns out if your x belongs to PZP, then this sort of infinite sequence will converge to a number, a p-adic number, and turns out somehow like after the second term, these will be always divisible by p. Therefore, it will be one. This will land in 1 plus PZP. Moreover, this sort of will turn addition into multiplication. So Keith suggested a slightly different way to see this. Maybe I'll say that in a bit. So there's a way to define the map in the other direction by taking the log of x. Basically, if you start with something which is common to 1 modulo p, which looks like 1 plus pa, and then you can just expand it again using Taylor expansions. So you have PA and minus PA squared over 2 and then PA cubed over 3 and go on and on. And this will converge as well. And therefore you have map both ways, and this will define an isomorphism between these two things. And definitely the log function will turn multiplication to addition, and the exponential will turn addition to a multiplication, and therefore get actually a group isomorphism maybe. Or maybe a topological group isomorphism. So Keith suggested some sort of a comment on this. So one way is to maybe feel like this is a little, how should I put this? It's a little not very hand-on. This is the way I wrote this. Keith suggested there's another way to write this map. Of course, it will be a different map, but still going to be isomorphism. The mapping going this way looks maybe a little bit more familiar to you. Sorry, excuse me. It goes like sending x to how should I put this? If maybe I should say sending maybe PA, which is going to be my x, to 1 plus p to the 8th power. And this is also a well-defined map. And we're going to do is in the exercise. I think in one of the exercises, I ask you to show that this type of things will converge, even if this will make sense, even if a is not an integer, just a p-adic number, this still makes sense. But these two are, in some sense, are actually roughly the same, in the sense that you can also rewrite this as in a completely formal way. That this is actually the same exponential of log of 1 plus p times a. If you think of it as completely formally, so in the real world, 1 plus p to the a is e to the log of 1 plus p times a. That's basically what we're doing. And log of 1 plus p is as explained over here. You just take this sort of Taylor expansion of this. And in fact, somehow you don't have to take 1 plus p, you can take it 1 plus 2p or 1 plus 3p. Anything you want, as long as it's sort of, if you take 1 plus p squared, it'll be different. It'll be very different. If you take sort of 1 plus something invertible in p and then times p, then you essentially get roughly the same thing, basically off by a multiple of a in some sense. Right? If you compare this exponential x and this thing here, they're off by, some number like log of 1 plus p over p, a multiple of this. So these short map are essentially the same up to some small things. He's also suggested that somehow another way to think of this through exponential is that somehow in this p-adic world, the number p or anything divided by p is considered very small. Just think about, in the real world, your x is now a kind of very small number. If you do this sort of Taylor expansion, this will kind of converge. And in fact, in the real world, it doesn't matter what the real norm of x is. It will automatically converge in the sense that, for any x, this Taylor expansion will converge. The reason is that, in the long run, you're dividing a n factorial here. This in the real world is very good because you have a number divided by a huge number in the denominator. Therefore, the absolute value becomes very, very small. So this converges very fast. On the other hand, in the p-adic world, dividing by something is not that good. If you divide by something, turns out if you have, especially if you have p in the denominator, if you divide by that, the p-adic norm will get large. So therefore, having this n factor in the denominator is not a good thing for you. It actually works against you. It turns out that this Taylor expansion you have over here in the p-adic world, this maybe I just write. So this has a finite radius of convergence. The p-adic world. So that's another comment I want to make here. Right. Right. Maybe just give another example of this before moving on to the next kind of theorem I want to talk about a little bit. So, so yes, I was asked a question. What about if Hansel's lemma? What if the simple Hansel's lemma says if modulo p have a simple zero, you can lift all the way to zp a simple zero. But what if that simple zero condition fails? I give an example of like x squared x squared equals to 5 in Z5, and show that doesn't have a lift. But actually, in some cases, even if the simple zero condition fails, you might still be able to lift it all the way. Here's another example, maybe. Maybe consider x cubed equal to 1. Excuse me, maybe x cubed equals to 10 in Z3. And this, in fact, you can lift, of course, like if you mod 3, you see that x cubed equals congruent to 1 mod 3. And this is sort of this, like maybe I write it like this way. And therefore, but this is x1 minus 1 to the cube. So therefore, the 1 is not a simple zero, it's a repeated zero. But this one does lift, there is a lift of this to Z3. In fact, we can do it this way. So think about what we're going to do. Well, what we want to do, so let me do it somehow you can solve by Hansel's way. But I'm going to do it in a really interesting way. So what do I do with this? So let's see. What I want is that I want this to the 1/3 power, right? That's what I really want. So here's a game. So how do you do this sort of binomial expansion anyway? So this is sort of summation of all the I greater than or equal to 0 of what is this? So n choose I, x to the I, right? So that's how you expand it, the binomial expansion. Now I'm going to write the same thing. So I want to write, okay. So I'm going to just formally write sum of I greater than or equal to 0 of, now my n is 1/3. That's fine. Just write 1/3. Let's formally write it and then explain what happened. And then
Liang, I've lost you. I can't hear you.
Can't hear either.
Liang, can't see the screen. We can't hear you. Looks like he's completely dropped.
The screen is
Hello, Liang.
I think. Can you give me the ability to share the screen? For me to share the screen.
Yep.
Thanks. It's interesting that I can hear you. You told me that I'm lost, but when I speak, you don't hear me.
Yeah. Yeah, I don't know why.
Okay, so that's good. So where did I lose you?
I think you were about to start with the proof of the theorem, right?
No. I'm not. I'm explaining this.
You had boxed. You had written exactly. That's that boxed binomial expansion. That's where it stopped.
Okay.
Okay. I wrote this binomial expansion. Good. I just lost you for like a second or so. Okay. I was gonna explain why this is a converging thing, or rather, I should probably just say that what the thing is. This is what? This is just formula. You just write down I factorial in the bottom, and then you do 1/3 times 1/3 minus 1, and 1/3 minus 2. And then let me just get rid of this thing over here. Dot, 1/3 minus I plus 1. It's just that product. And it's an exercise to show that this 9 to the I will trump over these sort of denominators. And then and also this denominator is over here, and that gives you a converging sequence. So here's maybe a kind of a slogan that any sort of a formal expression you can write down, as long as this infinite sequence will converge p-adically, it's a valid expression. And all these sort of formal structures of like, for example, this to the third power is what you want it to be, continue to hold. So this is something interesting in p-adic world. Like you can use all these all these sort of crazy expressions to do things. Maybe I before I explain the next theorem, let me sort of stop here and then see if there's any question about these comments.
I don't see any questions, but if there are any, I'll let you know.
Sounds good. You can interrupt me anytime. Hold on a sec. So let me now explain the theorem here, which is that it's a structure theorem for ZP cross. So, excuse me. Okay. So first of all, I want to explain the first. So let's read it first. ZP cross, namely all the elements in ZP where P does not divide A, and this is form a group and a multiplication. And I'm claiming that you can break this thing in part into just a finite group Z mod PZ cross and an infinite group like this. Moreover, and OPP greater than 3, of course, and moreover, this 1 plus PZP, as we just somehow proved here by the theorem that this 1 plus ZP with multiplicative group is really isomorphic to PZP. But of course, you can divide by P always. So therefore, you get ZP plus here. So the latter part we already kind of explained as above. So this is already kind of explained. And now I have to explain this one. Maybe here's a kind of before explaining what this kind of convince you this is something that kind of works, is that there's also sort of a finite version of this. In the sense that if you take ZP, somehow ZP mod P to the N ZP cross, in fact, you can show that this is the same as, just ZP mod P to the N ZP is the same as Z mod P to the N Z. And this, what I'm saying here, this is a cyclic group of order P to the P minus 1 times P to the N minus 1. And we learned that if it's a cyclic group of this order, then this must be isomorphic to Z mod P minus 1 Z cross Z mod P to the N minus 1 Z. And what I'm doing here is that this multiplicative thing is really just this thing. And this kind of degenerates to this one because I'm using sort of a mod P to the N version of this. So this is sort of a finite version of what the isomorphism I have above here. But in fact, this isomorphism passed to limit. So let's explain this proof. So let's first of all recall that actually p minus 1 equals 1 has solutions in ZP cross. So in particular, this I have a way to embed back all the piece root unity. This is all the piece roots of unity. Excuse me, p minus 1 first roots of unity. My bad. Back to ZP cross. So this is the Teichmüller lift I talked about last time. It's called the Teichmüller lift. And also we talked about last time that this is sort of multiplicative. So therefore, this embedding here actually respect the group structure, and I'm going to take advantage of that. Now our goal is to relate these two. So let's write down the isomorphism between the two. So I want something in ZP cross. Oh, maybe I should point out, I wrote upper cross on the ring to mean invertible elements in here, and it's a group under the multiplication. So this, when I write this, I indicate that this is under multiplication group. So I want to construct an isomorphism this way. This goes as follows. So maybe go this way. Let's go backwards first. Let's start with something a bar, something here, and then something looks like 1 plus pb on the backwards. Basically, well, I mean this 1 plus zp is already in zp cross, and just have to make this thing into zp cross. So that's exactly a Teichmüller lift. So I just map to the Teichmüller lift of this times 1 plus pb. So I map this way. And then I want to go backwards, right? If I want to get isomorphism, I need to go backwards. I start with C here. And there's a natural way to
Liang, I can see your screen. I don't hear you.
I don't hear anything.
Hello? Hello? No, can't hear you. Hello, Liang. I made you presenter again. Sorry, I'll unmute you. Yeah.
Okay. You hear me now?
Yeah.
I can hear you too.
Okay.
Yes, thank you.
See the screen?
I can see the screen and I can see the notes.
Yeah. I apologize for this. bad.
Stopped hearing you when you started talking about the inverse map.
Okay. Wait. Okay. Starting from C.
Yeah.
The first one is definitely C mod P, and the next one I don't know what it is, but I wanted to make sure that the composition I get identity. Right. So let's solve this. What is X? X is so that when I multiply back, I get to C. So C must be equal to C mod P times X. So you know what X is. X is just C mod the Teichmüller lift of C mod P. Let's sort of explain this a little bit more in a more example way. So here's an example. P equals 7, and I want to write this isomorphism like this. Okay, so I want to say, for example, where 10 goes. So first of all, 10 goes to mod 7. This is the same as 3 mod 7. And what is this? Well, by definition, this is 10 over bracket 3, right? So bracket 10 is the same as that bracket 3. But what is bracket 3? Bracket 3, I think I gave last time the expression of this is roughly speaking 3 plus 4 times 7 plus something. Okay? But rather, I mean, like, I want to divide by this. I could do the division, but it's a little bit inconvenient. So maybe I note this. So this 3 times 5 is congruent to mod 7, right? So therefore, what happens is that if I divide 10 by this 3, that's the same. So this will tell you that 3 times 5 is the Teichmüller of 1, which is just 1. So therefore, 10 divided by the Teichmüller of 3 is 10 times Teichmüller of 5. So I have to recall what Teichmüller of 5 was. It was 5 plus 2 times 7 plus 3 times 7 cubed and so on and so forth. And then you just multiply them together. 10 times that. And that's your answer here. Oh, bad. And you can kind of see already that somehow if you multiply the first two terms here, that gives you 50, which is congruent to 1 mod 7. And then of course, let's switch back to later terms and you have to do the multiplication explicit. If you want to have an explicit expression of what this number is, I guess. So I hope this gives you some idea of what goes into this isomorphism. Maybe I'll stop here to see if there's any questions about this theorem. So this gives the structure of ZP cross. Let's recall that, in Keith's lecture, that ZP cross is a Galois group of the p cyclotomic extension. So it has some sort of a finite part and then some sort of completely looks like a ZP part. Questions? No questions? Okay. So that was somehow, I guess I'm a little bit behind my schedule. Let's see how far I can get to. I'll try to catch up or with people who still understand things, of course. So today I'm going to talk about. Oh, good.
Yeah, it's good.
Okay. So today, the plan of the third lecture was to start talking about so-called p-adic Banach space. Again, remember that our slogan is that many theories over R has their analogs over QP. So we're going to do this. So there's over R, there's so-called Banach space, also Hilbert space. We're going to make their analogs today. And also I'll talk about the very important thing, which is called Mahler basis for the continuous function of ZP. That's going to be very important for our later discussion. And if time permits, I'll talk about p-adic measures. We'll see. So let's first of all recall what Banach space over R means. And basically, I just tell you what it is. So basically, Banach space over R is a R vector space. It's infinite dimensional. Usually we talk about infinite dimensional vector spaces, of course. And it's complete with respect to a norm. You can talk about the norm there. Maybe talk about the example before giving the axioms. So I can talk about sort of continuous functions on the open interval 0 and 1. And so I can take a norm, namely it takes the maximum absolute value on this function between 0 and 1. So what does this sort of norm set? What kind of property does this norm satisfy? Well, if you have some number in R, you can multiply with your function by this number, then the norm will be multiplied by the absolute value of this number, of course. And if I have two functions, f and g, then the norm, I mean, in this case, it's just norm of f plus g is less than equal to the norm of, or the maximum value of f plus the maximum value of g, of course. And the third one is that if the maximum value of f is 0, of course, I would say f is 0. And of course, if f is 0, then of course maximum value is 0. So that's what Banach space over real means. So we can sort of essentially copy the same definition. Banach space over QP is again a QP vector space. Basically, these two are, so if you look very carefully, I think oh no, actually not. I thought I copy and paste the two words. But anyways, not quite. So p-adic Banach space V over QP is a QP vector space. It's complete with respect to a norm, which is just like what you have over here. It's a real value norm, but the vector space is over QP. And it's compatible with it's sort of multiplication by a p-adic number. So what happens? The norm will be multiplied by the p-adic norm. And the third condition is also essentially the same thing. And what distinguishes two cases is the second condition. Over here, we have the so-called triangle inequality. Over here, we have the stronger triangle inequality. Remember that in the p-adic world, we always use a stronger triangle inequality to, or maybe strong triangle inequality to somehow get a good way to converging. And also this is sort of adapted intrinsically to the p-adic situation. And well, I probably won't have time to talk about the so-called Hilbert space. I'll only say a little bit maybe later. But in the Hilbert space, when your Banach space has some sort of over R has some sort of inner product structure, you can take so-called orthonormal basis. In the p-adic world, we have something similar. We say, okay, if my p-adic space V has an orthonormal basis, some EI in V, if the following two conditions holds. First of all, I want to say the first condition basically is normal. I want all the basis vectors EI have norm 1, of course. And the next condition is some sort of normal. It's a basis condition. It's in a complete sense. In the sense that every vector V in V can be written uniquely. Uniqueness is somehow important. As a converging limit, somehow you want to write your V as a linear combination of the basis element. But your basis can have infinite many elements in the basis. So you should write some sort of infinite formal sum like this, where coefficients belong to QP. But of course, you want your infinite formal sum to be convergent in some reasonable way. So what that means is that there's a third condition later. What that means is that, for example, if I is indexed by the natural numbers, what we want is this norm of these coefficients go to 0 and integers go to infinity. So, or if you put it another way, in fact, the next description works in general. That means that if you fix any epsilon bigger than 0, then there are only finite many i's such that the norm of this AI is less. Sorry, my bad. It's greater than equal to epsilon. No matter if you fix whatever this epsilon, how small it is, there's only finite many terms where the coefficient is bigger than this epsilon. So therefore, if you want to converge, I guess somehow up to somehow a small epsilon, you just need to add finite many terms. And note that also I want to point out we have this strong inequality here. And therefore, the convergence condition is not somehow saying some sort of a sum of the remainder term is the norm is less than equal to 0, less than equal to some epsilon. But rather, as long as each single term is less than equal to epsilon, then their corresponding sum will also have norm less than equal to that epsilon. So this somehow the convergence is much easier in the p-adic world. So that explains the work. So the first term explains the normal. Next condition explains the basis. Now I want to explain ortho, what ortho means, orthogonal means. So it means that if you take the norm of this vector as written here, then that's just the maximum norm of the pi norm of all the coefficients. Because we know that like all but finite, so this norm of these AIs will go to 0 as I goes to infinity. So the max will always achieve at some AI. So I want to make a sort of quick remark that in some sense, this orthonormal basis concept is a p-adic analog of the Hilbert space. In the sense that in the Hilbert space, I have some sort of inner product structure, and the norm will satisfy. Oh, sorry, my bad. So plus norm v minus. Oh, sorry. Of course. Like if the two, excuse me. Yeah, if the two vectors v and w are orthogonal to each other, then the norm of v squared plus norm of w squared is v plus w squared. But now, orthogonal in the p-adic world would mean that if you take norm of v plus w, it's precisely the maximum of the two norms, normal two vectors v and w. In some sense, this looks like I think it looks more like a L1 space in some sense. And here's maybe a kind of a typical example of a Banach space with a orthonormal base. Let's see. So this, I'm gonna call it L1 because it looks like L1. It's a sequence of numbers, A1 ... through A, QP. I mean, this is analogous. Maybe I should, before doing this is analogous to this example I have over here. Over here, I have some sort of functions on between 0 and 1. But instead, over here, somehow I think of this maybe another way to write this is I have some function from the natural numbers to QP. So that's how it's the same as sequence of numbers in QP. But then I want my, oh, maybe not quite the same. Anyway, I want my limit of these numbers to the pi norm is limit goes to 0. And now if I have a sequence of these numbers, I want to define its norm for this L1 norm to be just the maximum of all these coefficients. Because the limit goes to 0, therefore the maximum is always achieved by something. And now if I do this norm, also normal basis will be this En, where this only 1 happens at the nth place, and the other terms are 0. And therefore, this sequence An will be just basically sum of An times this sort of standard, En, which is sort of 1 at nth place. And this norm is precisely the maximum of all the p-adic norms of these coefficients. And that's as defined over here anyways. Okay. So, right. So this is what p-adic Banach space looks like. Are there any questions about this before I move on? To give you a very, I should say, very non-trivial example of p-adic Banach norm, which is somehow very important for us later. Just concept p-adic norm, p-adic spaces.
No questions so far, but I'll let you know.
Sounds good. Thank you. So now let's move on to this particular theorem I'm interested in. So this is sort of the topic of this my lecture, series lectures, is about p-adic numbers on ZP. So I want to consider sort of a continuous function from ZP with values in on ZP with values in QP. That's p-adic functions on ZP. So this sort of looks like a continuous function from 0 to 1 with values in R in the real case. But I'm going to sort of do the same thing. And because and now I'm going to define a norm on this one to be the maximum value of this function. Well, I mean, when I say maximum value, I have to,
Liang?
value is in QP. Yes.
There is actually a couple of questions. So one question is, why is this similar to L1 and not to L infinity?
I thought L infinity means it doesn't have this condition. L infinity is like you just have the sequence and then you don't have this condition.
probably call it more like there's something called
Maybe I'm wrong.
C sub 0, or sequences that tend to 0.
Yeah, maybe C sub 0, I guess. Maybe this is a bad notation. C sub 0. Sorry, maybe this is better. Other questions?
Yes, I believe there is another one. I was wondering if there is an analog of Cauchy-Schwarz inequality in the p-adic world.
Cauchy-Schwarz inequality. Let's see. What is Cauchy-Schwarz?
That's the one about dot products. I don't think so. There is no.
No, I don't think so. I mean, so here's maybe the difference. Like in Hilbert's. So the point is that it's very interesting somehow. I think about it. So what is this? Hopefully I don't get it wrong. It'll be very embarrassing. So this is if you have a Hilbert space, right? This is the inequality you have. Is that right?
That's correct.
That's right. This kind of thing doesn't happen in the p-adic world. So basically, this is kind of replaced by this condition in some sense. Somehow. So you don't have this inner product thing. You just so the orthonormal means this. They're somewhat different, I guess. But all the properties seem to be okay. Yeah, I mean, we see that somehow there's a theory over R, there's a corresponding theory over QP, not quite always the same. There's always something you have to change, of course.
Great. The person says that, thanks, that makes sense.
Yeah. So yeah, so this is somehow I guess it's sort of the good. If you think about it in over R, Hilbert spaces are good Banach spaces. Somehow over QP, the ones with orthonormal bases are the good p-adic Banach spaces. Somehow. Okay, so let's back to this. So I want to say, okay, so continue the function ZP with values in QP, and then the norm is the maximum value of this, meaning that you take the value of f at some points, and then takes p-adic norm of that, and then take the maximum of those. I want to say this norm is well defined because ZP is compact, and therefore I guess this FZP will be some sort of bounded space in QP, and therefore this norm is always sort of achieve its maximum. And you can see that this is a Banach space. You can we'll see it in a minute. We'll check each one of them. This is a Banach space, and somehow the content of the theorem is that this has orthonormal basis. This is the content of the theorem, and it will actually give a orthonormal basis of this. This is so-called Mahler basis. Let me write the name here. I'll write it again later. Okay, so let's quick check the properties of Banach spaces for this space. First of all, it's complete for the norm. Looks like so. I mean, right? You have a sequence of, if you have a certain sequence of functions where the maximum value of this where the pi norm of the maximum pi norm of the values somehow is used to uniformly is sort of converges or something. And anyways, so this is easy, I guess. Maybe I should write something. Sorry. So you have some sort of fi such that somehow if you have sort of a norm of fi plus 1 minus fi going to 0, then fi must converge to some f, right? Because this will tell you that the difference between fi plus 1 and fi will be, sort of uniformly goes to 0. Therefore, you can, at least value-wise, they all go to f, and then uniform convergence will tell you this limit is also continuous. And the second condition is obvious, of course. You multiply every term by some number, and there you go. And this is also follows from the triangle inequality from each particular values of this. And norm being 0 means that all the pi norm at each value at each point is 0, and therefore it's just a 0 function. So this is very easy to show. It's a Banach space. But let's sort of talk about the orthonormal basis. Maybe to note that somehow if I want to get orthonormal basis, the first thing I have to find is that I want something norm being 1. So what I mean by norm being 1? I mean, or maybe norm at least less than equal to 1, say. What that means is that all the FA, every A in ZP, this norm is less than equal to 1. In particular, that means the F of A belongs to ZP. So that's why I asked the following question. Can we, I mean, for the minimum, can we find some examples of continuous function on ZP whose value lies in ZP, right? So that I can, at least find some candidate of these spaces anyways. So let's try to, think about something. First of all, polynomials with integers coefficient, of course, great. And some power series, for example, exponential px, but don't like that. Of course, they take values in ZP. But if you think about it, this is really kind of a limit of these sort of polynomials. So maybe I'll stick with the polynomials. Those are somehow relatively easier. And of course, again, polynomials are a linear combination of these sort of powers. Great. So those are fine. But you know that we're working with p-adic worlds. Things can't be that easy. You can't just take polynomials to get things to work. And in fact, if you sort of take powers all the way up to x to the p minus 1, things should work the same way. But actually p, the p has to be something special. There has to be something to do with p, something, strange. So let's give you another polynomial, which doesn't have integral coefficient, but takes integral values. So this is a binomial coefficients. This is this function. Okay, so this is I want to say that this function takes value in ZP, despite you have a p in the denominator. So let's try to prove this. Let me just maybe get straight, just go straight to give you the great, the fantastic, anyways. So let's give a slightly not so easy to think about proof. So first of all, let me do two things. If x belongs to n, an integer, a natural number, of course this is an integer, right? Right. Any binomial number is an integer, of course. That's fine. The next thing I want to point out, this is a continuous. I mean, despite there's a denominator in p here, but it's still a continuous function. That's not a problem. The last one is that n is actually dense in ZP. We know that ZP is a completion, p-adic completion of the integers, but in fact, it's enough to take the natural numbers. And if you think about the p-adic expansions we write down, they're essentially limited positive integers. If you combine these three, you see that it's a continuous function. It takes value in ZP on the dense subset Z. So therefore, there's no choice. So it has, so this XP must be in ZP for every X in ZP. Because every X in ZP is a limit of positive integers. And therefore, X choose P, this function, will be a limit of sort of p-adic numbers. Therefore, it must be also two p-adic integers, and therefore will be a p-adic integer. So this is something kind of peculiar in some sense. You have p in the denominator, but still the polynomial will give you a number in ZP. But think about this. This proof doesn't really. If you look at this around the whole proof, there's nowhere use the fact that I'm doing x choose p. I can choose anything. So here's rate state of the theorem. 1 x choose 2, x choose n. Go on. This is an also normal basis of continuous function of ZP with values in QP. And this is called the Mahler basis. So in particular, every continuous functions f from zp to qp can be written uniquely as, let me write star for this equation, fx being sum of n greater than or equal to 0 of an xn with norm of an of p goes to 0. And I want to call this star. This is writing is called molar expansion. And maybe I should say that this is a very similar to Taylor expansion, a little bit. Except that somehow, in the real world, we're so used to talking about sort of polynomials and power series. But somehow, if you want to talk about sort of genuine p-adic functions on ZP continuous functions, like you see here, right? I mean, this powers, these monomials are not quite the correct thing. Turns out these binomial coefficients are somehow the correct thing to work with. It's kind of interesting, I think. Maybe I kind of stop here and see if there are any questions about like what we talked about so far, and after that I'll give the proof of this.
Let's give it a few seconds. I don't see any questions. Oh, there you go. Can you remind me what a Teichmüller lift is?
Take what?
Well, can you remind us what a Teichmüller lift is?
Teichmüller lift. Oh, that's
Yeah.
like earlier. The Teichmüller lift is wait, what? Right, this Teichmüller lift. So basically, this has a solution in here. If you start with an a here, then there's a unique solution to this equation here, which is congruent to this a modulo p. That's called this Teichmüller lift.
Maybe I can say that in my lecture yesterday, I did the Teichmüller lift for p equals 7. So the sixth roots of unity in Z7 come up.
Wonderful. Thank you for doing that.
I don't think I called it a Teichmüller lift, but I did find all the roots of x to the 6 minus 1 in Z7.
Teichmüller lift is some sort of fancy name.
Yeah.
Of course, works in general. I'm just getting used to it.
Yeah.
Okay.
Very
Sounds
good.
good. I continue then. Great.
Maybe
So
another like 5 minutes, Liang, or so? Or how much do you think you have?
Can I do 10? I'll try.
Yeah, let's do if you can do 5, good. If not, keep going.
Let me do 5 first. Sorry for running over. So step 1 is that, well, first of all, let's find what is an in terms of f. So let's assume this holds and then try to find these ans, right? So that's the whole point of this. Let's try to get this modular expansion. So what you can do is you can really let's assume this works. Let's evaluate x equals 0. Then you realize that, wait a minute, these are all 0 when x equals 0, right? There's only 1 here. Then you see that I already know what a0 should be. It's just f of 0. And the left hand says f of 0, and the right hand is just a0. And I can do the next thing, x equals 1. So on the left hand side, on the left hand side I get f1. On the right hand side I get a0 times 1, right? Plus a1. And then starting from 1, these will be 0. So I just have 2 terms. Therefore, a1 is f1 minus f0. I can do the next one. This will give me a0 plus, now x equals 2, so I have 2x1 plus x, and x choose 2. So I get a2. And the rest will be 0. So I can solve everything. Let me just tell you the answer. And you can imagine that I can repeat this and then really somehow got all these sort of all these values of an I want it to be. I want to find. So let's do it maybe more systematic way. So I want to define f. There are other ways to write this. So let me just do this f bracket 1. This is not a very standard notation to take the difference of this x. Okay, so it's a difference function of this x, and then I can take the n plus first distance to be the distance function for so this is sort of the distance function. This looks like, I mean, if you think about this, why is that? Okay, this is looks like this Taylor expansion. If you think about this, this looks like not quite not looks like, but this is analog of derivatives. Sorry, derivatives, right? So therefore, you know, and also maybe explain why I want to introduce this function. So if star is okay as this, what is f of 1? Let's see. F of 1 will be, I take the sum, I will get an. Now I have to take two functions that value the x plus 1 and x to take the difference, so x plus 1n minus x choose n, right? But this is by binomial equality. This is x choose n minus 1. And in fact, you can run induction and see that if you take the mth difference of this function f, that's just the sum of n greater than or equal to n, an, of x choose n minus m. Maybe I should say m greater than or equal to m. So now this really looks like, you know, if you compare small expansion to Taylor expansion, right? I mean, you're taking sort of mth difference, really. Somehow you basically, it looks like somehow you move these terms to the left, or somehow you truncate it a little bit. And even better, you can, and actually and then you can evaluate at x equals 0, and then get am is just basically f mth difference evaluated at 0. So this looks a lot like Taylor expansion somehow. But you use difference for the derivatives. So have proved that star is unique if it exists. I guess probably I'll just kind of stop here with the proof. And next, I'll pick up next time. I know I'm running over time. Sorry about that. And sorry about the connection issues. So next time I'll pick up the proof of this, and then say a little bit about the p-adic measures and so on and so forth.